So welcome again. And the last time we met, we had discussed probability theory and distributions. And we were to begin with handling of questions. So let's go to our handout. Let's go to our handout so that we can handle those questions. So in our discussion, we had talked about a rule known as Bayesian rule. We had talked of Bayesian rule. And from our handout, question number 1 says that consider 3 identical bags, A, B, and C. Bag A contains 2 gold coins. Bag B contains 2 silver coins, and bag C contains 1 silver and 1 gold. What is the probability of selecting bag A out of the 3 bags? What is the probability of selecting a gold coin from bag A? Now, when you're dealing with the Bayesian theory questions, the first thing is obviously to have in mind the formula, how the formula is stated. And we know so well the formula is just up there. We adjust a bit. Don't run away from that reflection that is there. Yeah, I think that is good. Then if you not see my face now, okay. Why? So we are saying we are dealing with the Bayesian rule. Bayesian rule. And in the Bayesian rule, as you can see the rule that is stated up there, we are going to use that rule. So having read the question is interpreted from where it has ended. And where it has ended is the probability of selecting a gold coin from bag A. So this is how you go about it. You say probability of a gold coin from bag A. So if you start A given gold, Now this one will be saying already gold has been selected. Already gold has been selected. And according to this rule, we are supposed now to open this one. And be able to say something like this, as you can see in the rule up there. It is the probability of gold given A, you multiply by probability of A, Now this one is, or maybe I could first of all have opened in a simpler way before I expand. In a simpler way, the simpler way will be probability of gold and A. That way, you divide by probability of gold. Divide by the probability of gold. Now this one, when you expand it, this, it opens up as probability of gold given A multiplied by probability of A. You divide by probability of gold given A multiplied by probability of A, or probability of gold given B multiplied by probability of B, or probability of gold given C multiplied by probability of C. Now this one is the possibility, or is giving us all the possibilities where you can find gold. So gold can be found in A, B, and C. So the argument then proceeds like this. If you look at the question, you'll be able to notice that we have 3 bags, and bag A has 2 gold coins. I also told you the other day that the probability of anything that you want is the desired over the possible. If you are computing probability, it is the desired over possible. So in this question, we are looking for gold in A. And we know that there are 2 gold coins in bag A. So the probability of getting a gold in A is 2 out of 2. And the probability of getting A is 1 out of 3 because there are 3 bags. Haya, hii ingine itakuwa 2 out of 2 times that. Now that is the probability of getting a gold coin in A, yeah, and the probability of getting bag A. Or when you look at bag B tunaambiwa it contains 2 silver. So in other words, it has no gold. Therefore, the desire of our heart, which is gold, is 0, you divide by 2 because there are 2 coins. Then the probability of getting bag B is 1 out of 3. Then when we go to bag C, it contains 1 gold and 1 silver. So it is 1 out of 2 and then 1 out of 3 to get the bag C. So solve that and give me the answer. Give me the answer. Okay, my camera is not very user friendly. Now give me the answer. I'm waiting for the answer. Two out of 3, that is from Ibrahim. Someone else to confirm? 2 out of 3. Sarah also confirms, that is good. So if they are confirmed, that is the answer. Let's go to the next question, number 2. When a machine is set correctly, it produces 25% defectives. Otherwise, it produces 60% defectives. The chance that the machine is set correctly is 50%. The machine was set, and before commencement of production, one piece was inspected and found to be defective. What is the probability that the machine was set up correctly? Probability that the machine was set up correctly. Probability that the machine was set up correctly. So in answering that, we can argue like this. Probability that the machine was set correctly, we can use SC to represent that. Set correctly, given what we found was defective. So as we have said in the other one, this opens up as probability of set correctly and defective. You divide by probability of defective. You divide by probability of defective. Now this one, when it opens up to look like this. Probability of set correctly given defective multiplied by probability of defective. Divide by probability of set correctly given defective multiplied by probability of defective. Or the other area we can get a defective is when the machine is set incorrectly. So we can use SI, set incorrectly, given defective, multiplied by, sorry. Sorry, that one has an issue, It should be the other way around. Probability of getting a defect given that we are set correctly, multiplied by the probability of being set correctly. You divide by probability of defect given we are set correctly, multiplied by probability that we are set correctly, or probability that we get a defect given that we are set incorrectly, multiplied by the probability that we are set incorrectly. Multiplied by the probability that we are set incorrectly. So as we said, this one is giving us the possibilities where we can get a defect. And we can get a defect when we are set correctly, and we can also get a defect when we are not set correctly. So if that is true, we can put the values. Then you will give me the answer. So the values are like this. We are told when the machine is set correctly, it produces 25% defectives. So the probability of getting a defect when we are set correctly is 0.25. And otherwise, it produces 60%. So 60% is the probability that you get a defect when you are set incorrectly. And then it continues to say, the chance that the machine is set correctly is 50%. So the probability that the machine is set correctly is 0.5, which now we shall come here. We say 0.5, that is the probability of getting a defect when we are set correctly, multiplied by the probability of being set correctly, plus probability of a defect given that we are set incorrectly is 0.6, multiplied by the probability of being set incorrect, it is 0.5. So work that out and give me the answer. Work that out and give me the answer. Okay, so what is the answer? Yeah, Irene says 0.294. 0.294. Someone else to confirm? Yes, Ibrahim confirms. So we go by that. So on your own, you shall handle question number 3. You shall handle question number 3 together with this question that I want to identify in the past papers. And I keep on telling you, you do the assignments. They are not compulsory, but they are very, very necessary. This is a question, like a simple one. Need to identify where it is hiding. Yes, this one of May 2014, question 5A. May 2014, question 5A. May 2014, question 5A. So you can try that also together with question number 3. So that is the first rule that we use to handle conditional events or dependent events. Now, the next one that we had mentioned that is used to handle is called contingency tables. Contingency tables. So let's now discuss contingency table. Now, contingency tables are simply tables that are used to handle dependent events. We can say these are tables used to compute probabilities of two dependent events. Now, each of the events or experiments, let's use also the word experiment. Each of the events or experiments must be divisible further. So when you're handling these conditional events or the experiments, they must be divisible further. The values in the cells represent intersection. The values in the cells represent intersection of sets and are hence connected by multiplication sign. Or are analyzed. I think the best word to use is they are analyzed. Analyzed by multiplication sign. They are analyzed by multiplication sign. The values at the totals, at the total cells are union of sets and are hence analyzed by addition sign. So those are some few points that you need to note about the contingency tables. We use them when the events are dependent. And these events or the experiments, they must be divisible further. So that we have columns and rows. The values that we find in the cells, they represent the intersections. And the values in the total cells, they present the union of sets. Therefore, we use the addition sign. We use the addition sign. So let's handle question number 4. Now, question number 4 says, the purchasing, rather, in a certain factory which employs 500 men, 2% of all employees have a minor accident in a given year. Of this, 30% had safety instructions, whereas 80% of all employees have no safety instructions required. Find the probability of an employee being accident-free. So we are going to draw a table. Let me design. I'm being called to address something. Let me design the table. Nione kama mtaweza kujaza. The table should look like this. So here I have total. Now there are two issues here. One is about the accidents. So someone was accident-free, we call it A, or someone had a minor accident, we call them B. And then we have total. Then we had instructions. And here, someone was given instructions, we call them C, and someone was not given, we call them D. So I would like you to try and fill the values. Now that you have been told in total we are 500, as you allow me a few minutes to respond to something. Yes. Have you managed? Let me give you the answers. We are told 2% of all employees have minor accidents in a given year. So 2%, so 0.02 times 500 is 10. So that tells you those who do not have the accident must be 500 minus 10, which is 490. Then we are told of this, 30% had safety infractions. So 30% of these who had minor infractions, minor accident, had safety. So 0.3 times 10, those are 3 guys. And therefore here, it must be 10 minus 3, which is 7. Which is 7. 80% of all employees had no safety infractions. So those who have not been given, it is 80% of 500. These are 400. So the balance here is 500 minus 400, which is 100. And therefore here it must be 100 minus 3, which is 97. And here it must be 400 minus 7, which is 393. Did you have those answers? Yes or no? Lynette says yes. What about the others? Irene said no. But Irene, now have you understood how it should have been gotten? Good. So I believe that everyone else has understood. Now let's do some other computations based on this. If you are told to get probability of A, you are told to get probability of A using the formula that I had given you earlier, that probability is equal to desired over possible. This is a formula that you must always keep on remembering. Desired over possible. When you are told to get probability of A, all the A's, they are 490. That is the desire. You divide by 500. That is the probability of A. You can leave it that way, or you can choose to simplify. Similarly, if I tell you to get probability of D, you got where we have D, they are 400, all the D's, and the possible is 500. So it is 400 out of 500. If you are told to give us probability of A and C, I told you the other day when we were looking at set theory, the word add means intersection. And in the notes we have written to Besema, the items which are inside the cells, they represent intersections. So if you are told to get A and C, you got where A and C meet. A, C, they meet here. So this is our desire, and our possible is this one. So that will be 97 out of 500. Similarly, if I told you to give me probability of B and C, probability of B and C is where they meet, B and C, 3 out of 500. If I told you to give me probability of B and A, probability of D and A, where D meets A, we have 393. You divide by 500. You divide by 500. The other thing is, if we are told to get probability of A given C, A given C, this one, what you do, you go to where you are told given. You go to where you are told given. You go to where you are told given. So we are given C. So you go to where we have C. C is 100. When you are there, you look for A. So the A's in C, they are 97. So this would be 97 out of 100. Will be 97 out of 100. Similarly, if you are told to get A given B. A given B. You will come where we have D. It is 400. When you are there, you look for A. In this 400, A's are 393. So it's 393 out of 400. Out of 400. If you are told to get probability of C given B, probability of C given B, you go to where there is B, B DOE, 10, and then you look for C there. It is 3. So 3 out of 10. Similarly, if you are told probability of B given D, probability of B given D, you go to where there is B, E. Then when you are there, you get the B's in D. There are 7. So 7 out of 400. 7 out of 400. So that is how you get them. That is how we get them. The other thing is, if we are told to get probability of A or B, probability of A or B, going by the rule that we gave, this one, the initial rule, this one opens up as probability of A plus probability of B, you minus probability of A and B. Probability of A and B. So this one, it is probability of A, nakibia huko unapata A ni 490 out of 500. That's probability of B, it is 10 out of 500. Minus probability of A and B, where A and B meet. What happened? You realize that A and B do not meet anywhere. A and B do not meet anywhere, so that is 0 out of 500. Give me the answer to that. Make sure you mute yourself unless you are speaking. Ibrahim says it is 1. Good. Yeah. So now, if we are told to give us probability of A or C, probability of A or C, it is the probability of A plus probability of C minus probability of A and C. Probability of A and C. So probability of A is 490 out of 100. I mean out of 500. plus probability of C. You got where we have C is 100 out of 500 minus probability of A and C, where A and C meet. We have 97. So 97 out of 500. 97 out of 500. So give me the answer to that. $493. I think I've muted everyone. Irene, I've muted everyone. Now, yeah, 493 out of 500. Okay, good. 493 out of 500. 493 out of 500. Good. Yeah, let's see that, Irene. So those are some of the extensions or what we have done so far. I was trying to show you some questions that you can be brought or you can be asked to do in regard to the table. Let us now provide the solutions to what the examiner had wanted in that question. What the examiner had wanted in that question. So Tadika solutions. Tadika solution. Solutions. So the solutions are: find the probability of an employee being accident-free, given that he had no safety instructions. So probability of accident-free, given he had no safety instructions, given that he was not given. He was not given the safety instructions. So as I've said, you will go to where it is not given. This one. And those who are not given is 400. When you are there, you get those who are free. So those who are free, they are 393. So that is 393 out of 400. 393 out of 400. $393 out of 400. The next one is the probability that he had the instructions. So probability that he was accident-free, given that he was given. Give me the answer to that. Someone was free, given that he was given instructions. Yes, is it 93? Ibrahim, someone else? Yes, yes. Yeah, good. It is 97 out of 100. Good. That they should be given. That's good. Let's now go to question 5. Question 5 inasema the purchasing department has analyzed the number of orders placed by each of the 5 departments in the company by type for this financial year as given in the table below. We have all that. Now, an error has been found in one of these orders. Determine the probability that the incorrect order was not for consumables. So give me, so that's why we don't have to draw the table again. We just go straight. Give me the probability that it was not for consumables. It was not for consumables. Give me that, and then you tell me probability that it came from maintenance or production. Maintenance or production. Maintenance or production. Give me those 2 answers quickly so that we can now look at probability trees. What are the answers? Good people, where are the answers? It was not for consumables. So if it was not for consumables, it was equipment, that is 15, or special, which is 7. You divide by 60. That is the answer. 50 out of 60. That's how it should have been, Irene. It came from maintenance or production. So maintenance is a total of 7, or production is 17, and again they don't meet anywhere, so there is nothing to subtract, so you divide by 60. Yeah. So that is all. It's that simple. If we are okay, can you type yes? If you are not okay, you raise your concern so that I proceed. Yeah, I can see the S's. The others? Okay. So after you revise those, you will have this one of December 2012, question 2C. December 2012, question 2C. The next area is called probability trees. Probability trees or probability tree. Probability tree. And we write that this is a diagrammatic presentation. Is a diagrammatic presentation of independent events. Independent events or independent experiments. You can put experiments and their outcomes and probabilities. And probabilities. It's a diagrammatic presentation of independent experiments and their outcomes and probabilities. The other point is that experiments do not share. Experiments do not share starting points, but events do. Experiments do not share starting points, but events do. Events along the tree, are intersections. While down the tree are unions. Events along the tree, as you move along from left to right, they present intersections. And if you are moving from top down, they represent unions. They represent unions. They represent unions. So that is how we go about it. And I want us to answer our question number 6 in the handout. Question number 6. It is saying that in the past, 2 building contractors, A and B, have competed for 20 building contracts, of which 10 were awarded to A and 6 were awarded to B. The remaining 4 contracts were not awarded to either A or B. 3 contracts for building of the kind in which they both specialize have been offered for tender. Assuming that the market has not changed, find the probability that all those. Now, anytime you read a question like that, the first thing is to come up with a sketch. And the sketch is like this. There are 3 experiments or 3 contracts. Now, the first one can be given to A or B or no one. The second one can also go to B, A or no one, A, B or no one, A, B or no one. And the third one will also behave the same way. So this is where we have the first, this is the first, this is the second, this is the third. So look here, how we count is each of these 1, 2, 3, 4, 5, 6, 7, 8, 9. Now each of these 9 will give us 3 more. Will give us 3 more here. 3 more that way. Will give us 3 more. So if you say 3 times 9, that gives us 27. So we are going to draw a tree that has 27 tails. We are going to draw a tree that has 27 tails. So I want you to go to a fresh page. Go to a fresh page. Go to a fresh page so that I direct you on how to draw. Go to a fresh page. Now, if you are there on a fresh page, you go to where they are ending, the end of the page. The end of the page. Upange 27 tails, small circles, like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So you draw 27 tails that way. After you draw 27 tails, now look here so that you have an idea. Hii ndio tunataka kuweka pale nayo ikiwa a fair copy. So tutaanza kuchora lines ikirudi huku. So hii space tunataka kuwekelea hii ikiwa yote. So we are going to have the third experiment here, the second one here, and the first somewhere here. So I've said the first point, wekelea 27 tails on a fresh page. 27. Shaweka hivyo tuende kazi. And make sure you are fast. So ukishachora hivyo huwa zinashikanishwa 3 of them. Remember we have said there are 3. So this one naweka kasako hivyo. You connect the 3 of them. Then hapa have kasako. And we connect so 3, 3 that way. Then so that is how it's drawn. So this is what we are saying: A, B, or none. A, B, or none. A, B, 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 none. Then these probabilities, we are told 10 were awarded to A. So 10 out of 20, that is 0.5. 6 were awarded to B. So 6 out of 20, that is 0.3. And 4 out of 20, that is 0.2. So those probabilities work hapa. This is 0.5, 0.3, 0.2. 0.5, 0.3, 0.2. 0.5, 0.3, 0.2. Even here, 0.5, 0.3, 0.2. 0.5, 0.3, 0.2. 5, 3, 2. 5, 3, 2. 5, 3, 2. 5, 3, 2. 5, 3, 2. 5, 3, 2. 5, 3, 2. So get up to that point. Once you get there, you write for me the word finished, so that I'm able to proceed from there. If you have a query, you also raise it. And be fast so that we try to finish before the time is over. 3 people have finished. The others? Good. I think we are finished. Therefore, we can try to answer the questions. So the first question is then, what is the probability that A will obtain all the three? So if we are told to get the probability that A will obtain all the three, A will obtain all the three, we are looking for the that is A now, obtaining all the three. It is the probability that A gets first, gets second, and gets the third one. That way. So if you follow that route, A, the answer will be obtained as 0.5 times 0.5 times 0.5. So give me the answer to that. $0.125. Let us go to B. We go to B, tunaulizwa B will obtain at least one contract. So hapo tunataka everywhere where there is B. And because B's are more, it will be the same as 1 minus probability that B gets none. B gets none. It will be easier that way. Probability that B gets none. So B gets none. B gets none. B gets none. So we start looking for where B has nothing. So it is A. That's the first one. It is the probability of A. Hapo hakuna B. The next place you don't have B is AAN. So probability of AAN. The next place is ANA. Hapo hakuna B. Probability of ANA. The next one is ANN. Because hapa kuna B, so probability of ANN. Hizi zote zenye zimefuata hii, this B, hizi zote ziko na B because of this one. So hizo zote tunaruka. Kuja hapa. So hii ni NAA. Probability of NAA. Probability that the next one is NAN. NAN. Plus probability of N or E, this NAN, we already have gotten it. So hizi zingine tatu zimefuata, they have a B. So NNA plus hii ingine NNA ndio tumeweka NNN. That is n, n, n. N, N, N. So those are the ones that do not have so I will then say this is equal to ama sasa tuweke tuseme 1 minus kwanza kuweka hizi venye zimefuatana these probabilities. Are we up to that point? If we are already here, say yes. Yeah. Good. We are there. So let us now start putting the value. So nimerudi hapa 1 minus probability of B gets none. Hizi ndio za none. So A, we already have that is 0.5 times 0.5 times 0.5 plus hii ingine 0.5 times 0.5 times n is 0.2 plus nikuja hapa 0.5 times 0.2 times 0.5 hiyo hii, then nikuja kwa hii 0.5 times 0.2 times 0.2 alafu hii ingine 0.2 times 0.5 times 0.5 then ingine plus 0.2 times 0.5 times 0.2 plus 0.2 times 0.2 times 0.5 plus 0.2 times 0.2 times 0.2. So, and if you want to know that you have not made a mistake, unahesabu hizi zilikuwa ngapi? 1, 2, 3, 4, 5, 6, 7, 8. Alafu unahesabu hizi 1, 2, 3, 4, 5, 6, 7, 8. Good. So work out that and give me the answer. As soon as you get it, let me have. The answer. Yes, Ibrahim says 0.657. Yeah, I can see Sarah, I can see Irene. That is good. So that is good. Yes, next. I can see that. Okay. Sasa, let's quickly go to part C. Part C. Part C, tunaambiwa two contracts will not be awarded to either A or B. So if you are told two contracts will not be awarded, if you are told two contracts will not be awarded, it means that only one contract will be awarded. Only one contract will be awarded. And that contract could be the first contract. So you will argue like this. The first contract is awarded to A, the second is not awarded, and that is not awarded. All that becomes plus. The first contract is awarded to B, the second is not awarded, and the third is not awarded. That is now when the first contract is awarded. Assume it is the second contract that is awarded. So we will argue the first one is not awarded, but the second goes to A, and the third goes to no one. Or the first is not awarded, the second goes to no one, the second goes to B, the third goes to no one. These two are when the second contract has been awarded. Or the first one was not awarded, the second not awarded, then we have the third one awarded to A. Or the first one not awarded, the second not awarded, but the third goes to B. So if that is true, then you will argue 0.5 times 0.2 times 0.2 plus 0.3 times 0.2 times 0.2 plus 0.2 times 0.5 times 0.2 plus 0.2 times 0.3 times 0.2 plus 0.2 times 0.2 times 0.5 plus 0.2 times 0.2 times 0.3. So that is how it will be solved. So work on that and give me the answer. The answer? $0.096. That is from Ibrahim. Second person to confirm so that I solve the last one. Yeah, Sarah confirms. So that is good. So the last one, we are told A will be awarded the first, B the second, and A will get the third. So that one is very simple. It is A getting the first, B the second, A the third. So it's that direct. So it is 0.5 times 0.3 times 0.5. Give me the answer. Zero 0.075. According to Ibrahim. Someone else to confirm? Yeah, Lynette, that is good. So with those two answers, we call it a day at that point and hope to pick up from there. So thank you so much. See you in the next lesson.